Hello, everybody. I'm trying a new app this time called Screencastify, so hopefully this will be better at the recordings. But anyway, let me hide this thing. All right, so we're starting with section 4.2, and this one's not too bad. But anyway, let's get started. So we're going to start with how to plot sine and cosine, but this time we're going to do it a lot more quickly instead of the forever that it took us a couple weeks ago. And there you go. Dropbox added 2 files. Fantastic. Okay. Anyway, so to quickly graph a trig function, it's best to only focus on the peaks, valleys, and x-intercepts of the graph. So that means in this graph, we're only going to focus on this point, the peak, x-intercept, valley, x-intercept. Here we have a peak, x-intercept, valley, x-intercept, and another peak. All right? And so where are those points located? So here, the critical x values are x is equal to. We can see that an x value is at 0, then at pi over 2, then at pi, then at 3 pi over 2, and then finally at 2 pi. And then we have another x-intercept, or for the cosine graph, you have x equals 0, pi over 2, pi, 3 pi over 2, and 2 pi. All right? As you can see, what will happen is this divides the graph into regions. And really the regions represent each quadrant. Okay, same thing over here. Right, and so each of these regions is pi over 2 across. Now, as we start moving the graph and squishing it and stretching it, that's going to change. But there's always going to be 4 regions, equally spaced. All right, as you can see, this divides it into 4 equally spaced regions. Yay. All right. So if we move on to create a sketch, whenever you're sketching, all we need is those 5 points. Okay, 5 points to create 4 spaces. So remember, it was 0, pi over 2, pi, 3 pi over 2, sorry, and 2 pi. And here, notice the graph is 2 cosine of x. And so, one thing I want to notice, if we go back to this picture, the y values for sine, and this is something that you don't use all the time, but it's kind of useful to know. But sine starts at 0, and so it goes up to 0, 1, 0, -1, 0. And the y values for cosine start out at 1, 0, -1, 0, 1. Okay? So I'm going to do that. The y values are 1, 0, -1, 0, 1. But notice that that was just for cosine. Now in my graph, it's 2 cosine x. And so there's going to be a 2 being multiplied to the whole thing. Sorry. Accidentally touched the screen. And so 2 times 1 is 2, 0, -2, 0, 2. And so we can quickly plot those points on our graph. So here we got 2, 0, -2, 0, and 2. And all we need is those points, and we're going to connect the dots. Now when you connect it, you have to make it look like a trig function. Don't be lame. It's not a V. And so I try to do like a lot of little lines so I can correct myself as I go. And there we go. So that's the graph of 2 cosine x. Notice that, what's the amplitude? The amplitude is now 2, which matches the 2 on the outside. All right, so keep on chugging. Sketch the graph of 4/5 sine of x. All right, so for this one I have, again, we keep our same critical numbers, 0. I need to figure out how that's happening so I can stop it from doing that. All right, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And notice that this is sine. And so the values for sine were just 0, 1, 0, -1, 0. But we're multiplying by 4/5. So there's a 4/5 around each one. Drawing. Okay, so what answer gets 4/5. No, sorry, 0, 4/5, 0. I keep on doing that. I apologize. I need to stop doing that. You know what? I'm going to turn off the screen. Nope, that's not it. There you go. And I'll have to use my mouse to move the screen around, which is going to take a while to get used to, but it's better than zooming in every 5 seconds. Okay, see, I already did it. All right. Anyway, so if we can plot these points, and we have 0, 4/5 at pi over 2. 4/5 is 0.8. And then we have 0 again, -0.8, 0. So notice that this graph, it's the same shape. It's just smaller, more compact. Okay, so what makes this one different from the other one is notice that this is positive 4/5, whereas this one is negative 4/5. So what does the negative 4/5 do? The only change that's going to happen, let me zoom out, is we still have our x values, so 0, pi over 2, pi, 3 pi over 2, and 2 pi. So the only change is, instead of being multiplied by 4/5, it's going to be multiplied by negative 4/5. So that means all the y values change. They just become negative versions of themselves. So instead, it's going to be 0, negative 4/5, 0, positive 4/5, and 0. And if I plot those, that becomes 0, mm, mm, mm. All right, connecting the dots. All right, so if we look at this, you can see that these two pictures are pretty much the same thing, except that they're flipped around the x-axis. So we have the x-axis, and if you multiply it by a negative, all that happens is the graph flips around it. Okay, so what was a peak is now a valley. What was a valley is now a peak. Anyway, so we can summarize everything here. Oh, and by the way, if you look at this, what's the amplitude of each one? The amplitude of the one on top is from the middle to the edge, from the middle to the peak or the middle to the valley, and that's just 4/5. Whereas for the same one here, the distance from the middle to the peak or the middle to the valley is also 4/5. So we can make an assumption here about amplitude. Generalizing the results in the previous 3 examples, we can say that if the graphs of through a cosine x and a sine of x, okay, we'll have amplitude of absolute value of A. And if you notice, the range on these is just from the peak to the valley, or from the valley to the peak. And so the range will be bracket, negative absolute value of A, comma, absolute value of A. Okay, so we do the absolute value so we don't have to write two different ones. It's really annoying to say, if it's positive, do this, and if it's negative, do that. So instead, if you use absolute value, you only have to write it once. But anyway, also, if A is less than 0, meaning if A is negative, then the graph simply flips across the x-axis. And that's it. Okay, so I have this on Desmos to kind of show you. So if I go to Desmos, right, so here I have a graph. Oh, projector mode's on. And I'm going to hit play. Keep on forgetting that I turned the screen off. And so here, notice that the amplitude is currently 0 to 1. If I hit play, so as A gets bigger, the graph just multiplies by whatever it is. So it's being multiplied, and when it's 2, then the graph jumps up to 2. I can change this really easily, make it 3. And notice the graph becomes 3. So whatever the number in front of the equation is, and you know what? I've never used the tools on Screencastify. They said that they can let me draw. Let's try that out. Oh, that is so awesome. Anyway, so notice that the number there, whatever that number happens to be, that happens to be the amplitude. So the amplitude is from here all the way to there. That is really cool that I can draw on the screen like that. When. So that's the amplitude. And, nope, doesn't let me erase though. I have to click on the eraser. But anyway, so if A happens to be small, let me go back to the clicker. So from 0 to 1 instead, then I hit play. And notice the same thing happens. It's just that since the number is less than 1, it's getting smaller. When you multiply by a number smaller than 1, the answer gets smaller. Okay? And then finally, if it's negative, all that happens is the graph flips around the axis. So 1 goes down to 0, and then it flips. And you have the opposite picture. So regular picture, negative. Regular, negative. All it does is it flips across the axis. Anyway, going back over here, let's finish our notes. All right, so adjusting the period. So now that's the vertical movement. Now we're going to do some horizontal movement. And this stuff is a little harder. The concepts are a little harder to grasp. So whenever a multiplier is inside a trig function, okay, and what I mean by inside a trig function is sine of blah, cosine of blah. Whenever you have the x and stuff inside the function, okay, the shape of the graph is horizontally stretched or compressed. All right. So if I look at this picture, you can see that this is a graph of sine of 2x. And notice that a period has changed. The period's where it repeats again. So we got the graph going, and it goes up to there before it starts to repeat. Okay? That means that the period is just pi. Now the size of each region is the size of each quarter. Remember, the quarters were the x-intercepts to the peak, x-intercept to the valley. And so the size of each quarter, instead of being pi over 2, the size of each quarter is now just pi over 4. Okay, so the size of each region is just 1/4 times pi, and that gives you the pi over 4. Now for sine of 1/2 x, and notice that this graph we would say that this is compressed. Which may seem odd because the number in front is a multiplier. So the inside, it kind of works the opposite of what you would think. It's a 2, and so you think that the 2 would make it bigger, but it actually compresses the function. Now we have a 1/2, and you're going to see that this is stretched. Okay, because if you look at how long it takes to repeat, it takes 4 pi for it to repeat again. And then again, same idea as before, 1/4 times 4 pi is pi. So that means each of the quarters in this case are going to be pi across. Okay, so each cycle is always going to be split into 4 quarters. So the cycle is just how long it takes to repeat, and the quarter, just multiply whatever the size is by 1/4. So the period was pi, multiply pi by 1/4, pi over 4. The period was 4 pi, 1/4 times 4 pi is pi. Anyway, so before we start, I want to show you again on Desmos. So if I go back to Desmos, I can click on this picture, transfer vertical, this one. Yes. All right, and so this one's a little more on the side. Ignore the stuff on the left, but I want you to focus on the graph here. We have a sine wave caught between 2 bars, and here, what moves the bars is the variable c here. So yay, I can write on the screen. That is so cool. Okay, so this c is what controls the bars. So if I go back and I hit play, I'm just going to move the thing. Notice that as c gets bigger, it gets crushed between the 2 bars. Okay. Notice the cycle. I mean, there's more than one cycle here. But notice that the points that it's touching don't change. And then we just kind of squish it. The closer it gets to infinity, the more it's going to squish. So the bigger the number, the squishier it gets, the smaller the period. Bigger the number, smaller the period. And then we can go the opposite way and go 0, and instead of 20, make this a 1. And the smaller the number, let me click off the screen. So now the smaller the number, the more spaced out it gets. Okay, I'll link these to Desmos so you can play with these graphs if you want to get more of an idea. And I'll try to clean this up so you know that only to mess with the C and not the others. But anyway, so how do you find your new period? So whenever you're trying to find a new period, notice that the original function, when you're not messing with it, remember sine of x is the original. The original is between 0 and 2 pi. So it turns out that whenever you want to mess with it, whatever goes here on the inside has to go on the inside here. So if I say what's the period of sine of 2x, this is just 0 is less than or equal to 2x, because that's the inside. And notice that I can divide everything by 2. And so this gives me 0 less than or equal to x less than or equal to pi. And so if I look at this as my answer, I can see that my period is pi. All right. I need to make these pens thinner. I'll do that for the next lecture. Anyway, so period of sine of 1/2. This is just 0 less than or equal to 1/2 x less than or equal to 2 pi. And here we would multiply by 2. So you would say times 2 times 2 times 2. And if you do that, you get 0 is less than or equal to x is less than or equal to 4 pi. So if I look at that instead, let me undo. Where's the undo button? I haven't used this app in a bit. Oh well, I'll erase it. No. Okay, so you can see that here in this case, the period would be 4 pi. So whenever you're unsure of what the period is, all you do is whatever's inside the trig function, sandwich it between 0 and 2 pi, and solve for x. And when you solve, the left and right bounds will give you the period. Anyway, so for an example, find the amplitude and period of 2/3 cosine 7/4 x. So looking at this, we can see that we have this number, and this number gives me the amplitude. It's the number in front. So I know my amplitude is the absolute value of 2/3. I know that's kind of silly, but remember the amplitude can't be negative. So if it was negative, you make it positive. So my amplitude is 2/3, and then the period. And so for the period, notice that I have 0 less than or equal to, the inside of the graph is, inside of the cosine is 7/4 x. And so all I'm going to do here is multiply everything by 4/7. Okay, 0 times 4/7 is 0. 7/4 times 4/7 is 1. They cancel each other out. And then 2 times 4/7 is 8. So this is 8 pi over 7. Right? And so the period here is just 8 pi over 7. Okay? Now what would you do if they wanted to find what the length of each quarter was? Remember when we were graphing it, you need to know the quarters because they tell you where to put your peaks and your valleys. So I kind of didn't give myself enough room here, so let me kind of write it to the side. So the length of each quarter, and again, this is going to be useful when you're graphing, it's just 1/4 times the period. So 1/4 times 8 pi over 7. Okay, so that's 8 over 4 is 2, so that's just 2 pi over 7. That means that if you were going to create a graph and you made your axis, then this would be 8 pi over 7, and then each quarter would be 2 pi over 7. And so we'll notice that this is cosine. So cosine starts up here. And so you can create a really quick sketch. So that's the idea of the quarters. They help you graph where your x-intercepts and your peaks and your valleys are. Anyway, let's move to the next page. Almost done. So we're going to generalize the period because sometimes some people hate having to solve it every single time. So for any real number b greater than 0, remember that when they say b greater than 0, they're just saying that it's positive. The graphs of sine and cosine will have period, okay, and this is 2 pi over b. All right, now the reason for that is we just do what we've been doing. 0 less than or equal to bx less than or equal to 2 pi. Notice that all you would do is divide everything by b. And that gives you 0 less than or equal to x less than or equal to 2 pi over b. And so we can see that the 2 pi over b is the same thing as the period. Anyway, so the reason why we only deal with positive b, because if b is negative, we just simply use the even and the odd properties to change the equation. So sine of negative bx, you don't deal with the negative b. What you do is you just move it to the outside because sine is odd. And cosine of negative b, is even, so that just becomes cosine of bx. So you use even and odd properties to rewrite the equation when there's a negative on the inside. All right. So let's do an example. I'm going to do this one, and then I'll leave the next one for you to work on your own. But anyway, so this says graph one cycle of 4 cosine of negative 2/3 x, construct a frame using the amplitude and period, and divide it into 4 equal regions. So again, this part is how we're going to be graphing things now. Okay, you construct a frame. The top and bottom is the amplitude, the left and the right is the period, and then you split it into 4 equal parts, and you can graph whatever you're looking for. So anyway, looking at this, I can see that the amplitude is simply the 4 that's right there. Okay, that means that my graph is going to be between 4 and negative 4. Okay, so the amplitude tells you how high and how low it goes. It's going to go 4 up and 4 down. All right, so now the other part is the inside. And again, that's 0 less than or equal to negative 2/3 x less than or equal to 2 pi. You can use the formula if you want. I like doing it this way because it just, I don't know, I like doing it. So I multiply it by negative 3/2, negative 3/2. Let me put that negative 3/2 in front. Right? And so that's 0. Negative 3/2, negative 2/3 cancel. And then we got, oh, I did make a mistake. Bad Gilbert. What did I say about negative signs? Because that messes with things and that makes things more annoying. I apologize. So our first thing to do is notice that this is 4 cosine of negative 2/3. So cosine, this is an even function. And even means that I can drop the negative. So this really becomes 4 cosine of 2/3 x. I'm sorry. On the top half of the page, I said rewrite it, and then I forgot to rewrite it. So if we do this again, now I can multiply by 3/2, 3/2, 3/2. And this gives me 0, x. And then if I multiply that, notice that I get 3 pi. And so here, my period is equal to 3 pi, which means that the length of each quarter is going to be 1/4 of that, which is 3 pi over 4. Okay? So if I go to my graph, I know that this is going to be 3 pi over 4. Then we double it, 6 pi over 4. Then we have 9 pi over 4, 12 pi over 4. So the values here are going to be, the 6 pi over 4 simplifies to 3 pi over 2. 9 pi over 4 just stays 9 pi over 4. And 12 over 4 is 33 pi. Notice it ends with a period. So I have the 4 points that I want, and now I just look at the graph. I know that I have a cosine. Cosine of x is, well, kind of butchered it, but is that shape. So that means it's going to start up here. And there we go. So my cat just ran into the middle of the living room and belly flopped. That was really cute. Anyway, and so there's your graph. So the amplitude tells you how high and low to go. The period are your x values. You split it into 4 parts, and those 4 parts tell you where to put your peaks and your valleys, which will change depending on if it's sine or cosine. All right, so I got all that done. So go to the next page. So they say extend the graph from the previous problem. And so in this graph, we had 0, 3 pi over 4. I already forgot it. There it is. 3 pi over 2. Uh-oh. And we got 6 pi over 4, 9 pi over 4, 3 pi. And then we can keep going. The next one would be 13, 14, 15 pi over 4. And then 18 pi over 4, which is 9 pi over 2. This was negative 4 and 4. So my graph, the original graph that I had, was this picture. Same exact one that I graphed on the previous page. It looks skinnier because it's less of the screen. And all I got to do now is just extend it. So we just continue the pattern. So up here, we start up top, go to the middle, down, middle, up, middle, down. And you can just continue the cycle. Remember, each tick mark was 3 pi over 4. So if you were wondering what I was doing when I was creating those new numbers, I was just adding 3 pi over 4 in my head. All right? So that means that this is negative 3 pi over 4. You can simplify it, but negative 6 pi over 4, negative 9 pi over 4, negative 12 pi over 4, which is negative 3, negative 15 pi over 4, and then negative 18 pi over 4. So those were the numbers I was doing. I was just adding 3 and simplifying it in my head. 18 over 4 is 9 halves. 12 over 4 is 3. 6 over 4 is 3 halves. But anyway, so this next problem, number 7, I want you to do it on your own. Graph one cycle of 2 sine negative pi x from negative 3 to 3. And so on Canvas, there's going to be an extra link where you can click on it to make sure you did it right. But I really want you to try these on your own. So yeah, especially now that we're doing online lectures, you want to give yourself that practice. All right, and then the last thing here is applications. Again, I'm going to do the first one. The second one I'll leave to y'all. But anyway, so an application of this is any object or quantity that's moving back and forth consistently is said to be in simple harmonic motion. Again, I need to adjust the thickness of these things, but harmonic motion. So it can be used to model the equations. And you're going to see these when you get to physics, these equations. A is sine omega t, A cosine omega t. It's the same omega that we dealt with in the last section. So anyway, a mass attached to a spring oscillates upwards and downwards. So this spring is just going up and down. Anyway, from its equilibrium position after t seconds is given by the function blah, where d is measured in centimeters. What's the furthest distance from the mass of the equilibrium position? Okay, well, the spring, it starts off in the middle, and then the spring goes up. So here's time. And so in a certain amount of time, the spring goes up, and then the spring goes down. Then the spring goes up, then the spring goes down. Then the spring goes up, and it keeps on doing that. So when they say how far, what's the max distance, they're just looking for the amplitude. Anyway, I could continue to write there, but that's just making it look nasty. So furthest distance is just the amplitude. So from looking at that, we can see that the amplitude is negative, absolute value of negative 3.5. So that means that it's 3.5 centimeters. How long does it take to complete one oscillation? So when they're saying that, how long does it take one oscillation? All that is the period. And so here I'll use the formula. So the period is 2 pi over b, and the b here is also 2 pi. And notice it's the number that's in front of the variable. 1. So how long does it take? It takes 1 second. For one oscillation. All right, and that's really about it. So these word problems, they're not trying to make you actually do crazy math. They just want you to look at an equation that you'll see in physics or in chemistry or in any future application of math class, and notice that, oh, look, that's just a trig function, and you can figure out what the amplitude and what the period are. All right, so try this problem again on your own. It'll be in that video that I send you. It'll be in its own separate video. But anyway, that's it for this section. So hopefully it wasn't too bad. I'm going to try to make things better, like make the font a little thinner so my writing isn't so chunky. But other than that, let me know if you have any questions. Have a good one. Now see, now I got to figure out how to turn this thing off. I think I go here. Yep. All right. Y'all have a good day.